All right. Good afternoon, class. I hope everyone's doing well. Um, I woke up super late today, so normally I've been exercising before I give my lessons, but today I just basically rolled out of bed and then went live. So I'm a little bit groggy. I'm drinking some coffee. This is my coffee mug. You can see it's got a brown or a black Boston Terrier on one side and a brown Boston Terrier on the other. So it's the perfect coffee mug for me. As I was live streaming, I saw something else that was uh, pretty funny. So I'm going to show you the dog toy that my mom got my dogs for Christmas. It's this. So she obviously doesn't know about emojis, but it's pretty funny. So I thought I would show you guys. And look at the face on it. It's got a mustache. Bug, be quiet! Knock it off! All right. So let's start talking about physics. This should be pretty simple lesson. Okay. So what we're going to talk about is energy stored by a capacitor. Okay. Yes, I do yell at Bug because Bug is my responsibility. He's 100% my responsibility, and so I will sometimes yell at Bug. Okay, Bug knows my angry voice. You guys don't know my angry voice because I don't think it's my job to yell at you guys that much. Okay, so we're talking about energy stored in a capacitor. So one of the things that I was talking about is how a capacitor stores charge and then it can release that charge in a burst of current. Okay. So what we're going to learn today is a formula for the energy stored in a capacitor. And so you might remember that the formula for electrical potential energy is Q times the electric potential. Okay? Now I'm going to write that. I'm going to write the electric potential as V because when we're talking about circuits, the potential is pretty much exclusively given as V. So I have U equals QV. And then let's suppose we add just a tiny bit of charge to a capacitor. That charge could be written as dQ because it's just a tiny bit of charge. So if we add just a tiny bit of charge to a capacitor, it's going to add just a tiny bit of electrical potential energy. So it'll be du equals dq times V. So then if we have our formula Q equals CV, this was the fundamental formula for a capacitor. We could imagine taking a differential of this equation and we would have dq equals C dV. Now, why is that? Well, dq, so I'm basically taking the derivative of this equation. The capacitance is constant because the physical geometry of the capacitor is not changing. Okay. So anyways, that's this formula I'm going to then plug in for dq. And I have C times dV times V equals du. Okay. Now what I want to imagine is gradually building up the voltage across the capacitor plate from 0 to some final voltage value. Okay. So basically what we're going to do to both sides is we're going to integrate both sides. The integral of du is equal to the integral of C dV times V. And so doing the integral on the left-hand side, that just gives us U, the total amount of energy stored in the capacitor. And then on the right-hand side, I can factor out C because it's a constant, and I just get the integral of V dV. So I've used the commutative property of multiplication to exchange those two, the V and dV, with each other. And you can see that this integral is just the same as the integral of x dx, which you know is x squared over 2. All right, so this integral is going to be v squared over 2. And so we get that the potential energy stored in the capacitor is 1/2 CV squared. So I move the 1/2 and I put it out front. All right. Now we can actually mix this equation with Q equals CV. So we could write, so basically we can take these two equations and mix them together and express the energy in terms of different variables. So what we can then do is write it as 1/2 QV. That's one way we can write it. Or we could write it as 1/2 Q squared over C. So I leave it as an exercise to the reader, or to the viewer, I should say, to get these two forms of the equation by plugging in the defining equation for a capacitor. All right? So, boom. These are our key equations for today. All right? So I'm going to flip over the page. And so now I want to answer the question, well, gee, what happens if we mess with the geometry of the capacitor? Okay, what happens if we mess with the geometry of the capacitor? So you might remember that the geometry of the capacitor is, the formula for the capacitance is C equals epsilon A over D. All right. So basically you could imagine, well, what would happen if we altered the distance between the capacitor plates? So if the distance between the capacitor plates gets closer together, the capacitance goes up. We could imagine, here's our capacitor plates, and we have like we make like an ice cream sandwich. You know, I might actually, I think I ate all my ice cream sandwiches. My emergency ice cream sandwiches are all eaten. But you could imagine an ice cream sandwich with just the chocolate cookies on the top and the bottom. And then we put in a dielectric between the capacitor plates. That would be like the ice cream. And we mess with the permittivity. All right. So these two things can change. So what effect does that have on the energy stored in the capacitor? All right. And so really it depends on while we're adjusting the capacitor, what is the capacitor hooked up to? So if we're messing with the capacitor and you should get some more ice cream sandwiches to show us. I went to Target and they were out of the ice cream sandwiches that I like. So they only had mini ice cream sandwiches. I like big ice cream sandwiches. And they only had the Neapolitan, like 3 types of ice cream sandwiches. And I like just the vanilla ice cream sandwiches. All right. So if you have a capacitor that is not hooked up to anything, then there is no way for if you have a capacitor that is just free, just by itself, there's no way for charge to get from one side of the capacitor plate to the other. So in this case, you would have Q equals constant. Okay? So that means if we go over to the equations here, while we're adjusting the capacitance, we want to actually use this equation, U equals Q squared over 2C. Why is that? Because if the charge is constant, while we're adjusting the capacitance, the voltage actually changes. Okay? So in this case, we want to use U equals Q squared over 2C. All right? But what if we are messing with the capacitor while it is hooked up to a battery? Okay? So here we're messing up with the capacitor while it's hooked up to a battery. A battery provides a constant voltage. So in this case, we have V equals constant. And in this case, as we adjust the capacitor, the charge on the capacitor plates can actually change because the battery will move charge from one side to the other while you're doing that. Okay? So in this case, charge is not constant, but the voltage is. So we want to use the version of the equation that doesn't have charge in it, which would be this one. All right? So for this one, we use 1/2 CV squared. U equals 1/2 as far as I know, this will be on the AP exam. I looked at which units were excluded, and they excluded magnetism but not circuits. As far as I know, this will be on there because this is part of circuits. Regardless, I'm going to teach you everything that is part of the AP curriculum. Okay, so we're using the equation 1/2 CV squared because a battery is going to fit. So now we want to ask the question, what if the distance between the capacitor plates goes up? Okay. So what would that do to the capacitance? All right. If the distance between the capacitor plates goes up, then we can see, based on this equation, the denominator increases, so the capacitance is going to go down. So this means that the capacitance goes down. So now, what effect does this have on the energy stored in the capacitor? Okay. Well, it depends on what we've kept fixed on the capacitor plates. So if the capacitor is all by itself while we're increasing the distance between the plates, then we can see, based on this equation, U equals Q squared over 2C, that we've reduced the capacitance, so we've reduced the denominator, which means that the energy would actually go up. So the potential energy stored in the capacitor goes up. One way to understand this is that the capacitor plates have equal and opposite charges, so they're attracting each other. And if you're pulling the capacitor plates apart, you would actually have to do work, right? It would take effort to pull these capacitor plates apart. And so the work that you do becomes electrical potential energy, okay? I'm going to divide these two scenarios. What if we reduce the capacitance with a fixed voltage? Well, in that case, we would use U equals 1/2 CV squared. All right, and the capacitance goes down, so therefore the potential energy goes down. All right, so notice how we get different conclusions for how the electrical potential energy changes depending on what we're keeping fixed on the capacitor while we make those changes. Okay, so that is the important part of what you need to understand regarding this. All right, so I think that's my lesson for today. It's a pretty quick and easy lesson. Hope you guys have a wonderful rest of the day, and hopefully I'll see you on Discord in about half an hour. All right, bye.